Right, so we continue from where we left off. There was a question, let me say a comment. Someone didn't understand the product of some way of coming up with the expressions from the Kano map. All right, I had just briefed how to identify expressions from two perspectives, sum of products and the product of sums. One, sum of products, we identify ones. The other one, we identify zeros. We just identified our zeros here. Now going to the expression. One way of understanding this is using these expressions I just gave you here. In blue, they represent product of sum. Then if I'm using sum of products, they will be like this: B bar, C bar, this is B bar, C. Here we have bar, bar, B, C. So this will be A bar. This will be A. All right. So in this case, we are using product of sum. So I'll deal with the blue ones. So for the first one, I already identified which variables remain constant and BC remain constant. How do I put BC in the expression? It is B plus C. Going to the other zero, which is a group of one, what remains constant? Both not both, A, B, and C remain constant. If you have one group of, if you have a group of one element, all the variables, they remain constant. The practice, it will make sense, believe me. So here I know all the variables are supposed to be there because it is a group of one. Now, here we have A, so it remains as A. Here we have B bar plus C bar. So this will be our expression for product of sum, which is equal to the one which we already did for sum of products. What was the value? Help me, help me. B bar C plus B C bar plus AC or plus AB. These two, these are sum of products, and this one is product of sum. These are the same. If you simplify this, it will remain, it will give you these answers here. Right, so those are two ways we can deal with and come up with minimized expressions of the Kano map. All right, and we move. We have limitations. The Kano map, it has its limitations. Kano map, it has its limitations. Right, one, it is only efficient for circuits which have a small number of bits, and it gets confusing for higher bit representation. Right, so if I'm using two variables, if I have a circuit with two variables, it means I have four outputs. It means four squares on our Kano map. If I have three variables, I have 8. 4, I have 16. 5, I have 32. Since you are using what we call hand computation, it's not the computer which does this, the Kano map. It's you. It gets more confusing as the number of variables increases. It's way easier when I have 8 outputs, okay? Even when I have 16 outputs, it's a very small number, but it gets difficult using hand computation. So that is one limitation of the K-map, is we have more variables in our circuit. It's time consuming coming up with simplified circuits. Or when we are building our IC chips, you realize You can have as many as 5, 6 variables. 1, 2, 3 variables. Those are for basic understanding. But when you are building bigger logic devices, you have a number of variables, which means a lot of output possibilities. And simplifying them using the kernel map isn't is efficient, right? Because of these limitations, that's why we have another way of minimizing circuits. We begin with Boolean, and we saw that as we increase the number of variables, it gets very difficult. We then got to the kernel map. Same reasons as we left the Boolean, we now have what we call the Queen McCluskey method for 4 plus variables. You can use it for 3, okay? But I think it will be much easier if you can use the kernel map for 3 and less variables. But for 4 plus variables, we have what we call the Queen McCluskey method. It is also known as the tabular method, and it's a more systematic way of minimizing expressions of large variables. It is suitable for both end computation, and it is also programmable, right? Programmable. Instead of using our hands and our brains leading to human error, with this one, you can make a program which minimizes your circuit. You just give it the min terms and it minimizes for you. Now, for the sake of learning, we begin with the end computation part. If we have programmers amongst us, inshallah, they can help us with how we can program this Queen McCluskey method. All right, before we begin, there are a number of terms which we need to define, which will be used for our tabular method. We have what we call the implicant. We have what we call the implicant. This is a group of ones. An implicant is a group of ones. For example, here, this is an implicant. Simple definition, a group of ones. It will make sense later on why we defined a group of ones. We have what we call a prime implicant. So a prime implicant is the largest possible group of one, largest possible group of ones. We have essential implicant. We have the essential implicant. The essential implicant. This is a prime implicant having at least one min term which cannot be combined in any other way. A prime implicant. So an essential implicant is a prime implicant which has a min term which can't be grouped. Right? An essential implicant is a prime implicant which has a min term which cannot be grouped. The same way we were grouping in the kernel map, I mentioned we need to start grouping the largest number of variables, largest number of ones That is our prime implicant, the largest number, largest possible group of ones. And we said we have the essential implicant, a prime implicant which has a min term. We know what a min term is. I wanted to define what a min term is. A min term is if we had three variables 0, 0, 0. This is min term 0. As we continue, we have min term number 7. So when we talk of min terms, this is a min term here. Now that we've defined those, we go directly. Best way to explaining the tabular method is by going through an example. All right. For those who are participating in this video, after this, we have an assignment due next Sunday. It's very important to take notes on what I'm going to say here to save your data, possibly, so that you won't need to download and redo these things. I'm going to go through the tabular method here. I'm going to give an example, then an assignment with another expression which needs to be minimized using this same method. Yeah, Kenya Banga. All right. Example, we have a four variables. It means A, B, C, D. 4 variable function, which is equal to a sum of min terms 0, 1, 6, 7, 8, 9, 13, 14, 15. Simplify that function using the tabular method, the Queen McGlasky method. How do we simplify it? Where to start? The best way to do it is to have a table. How many minutes do we have here? The thing is this 40-minute limit. It means if I draw my table, once the limit is there, to remove everything, why? Right. We have a table 1, 2, 3. Okay, let's start with this one. I remove this. All right, let's start with a table like this one. We start with identifying the min terms. For this value of 0 participation, what is the min term? What is the min term for the first value in the notation?
0, 0, 0, 0.
0, 0, 0, 0. That is our first min term. And for this one, the one, we have 0, 0, 0, 1. And for the rest, you do the math. Those are our min terms. You identify your min terms. We just identified them. All right. Step number 1. Group min terms in terms of ones present in them. Group min terms in terms of ones present in them. So we are going to group the min terms in terms of ones present in them. First column of our group, first column of our table, we have the groups. All right. So we'll start with groups with 0, 1s. Min terms with 0, 1s. All right, here are our minterms. We have 0, 0, 0, we have 0, 0, 1, 6. What is 6?
0, 1, 1, 0.
0, 1,
1, 0.
1, 0.
1, 0, 8, 4, 2, 1. So we have 7, 0, 1, 1,
0,
1,
1, 1, 1.
8, 9,
1, 0, 0, 1.
13, 14, 8, 12, 14, 15, 1, 1, 1, 1. All right, these are our minterms here. Step number 1, group minterms in terms of ones which are present in them. So if I look at minterm number 1, how many ones are present here? 0. So I have a group with 0 ones. That group, it has the minterms 0. Right. We continue with this one. How many ones are here? We have 1, 1. Here we have 2. Here we have 3. We have 1 here. We have 2, 3, 1, 2, 3, 4. Can I get an amen? I don't know my number paper.
Hallelujah.
Amen.
Amen.
All right. How many ones are in the midterms? There we have. So we have a group of 0 where we have only 1 term. We have a group of 1. This is 1. So we have these 2 in 1. 0, 0, 1. So we have, this is my group of ones. It's complete like this. What is happening? Okay. This group is complete like this. ¿Qué pasa? Okay. We have another group of ones. Help me. How many? What minterms? We have ones. I'm seeing my notes again. We have minterm. This is minterm 0, 1, 6, 7, 8, 9, 13, 14, 15. So we have minterm number 1 and minterm number 8. Group with 1 ones, we have minterm number 1 and minterm number 8. That's a complete group. That's a complete group. We have 2. Group number 2. This is 6, 9, 6 and 9. So we have 6 and 9. Very simple if you follow procedure. We have a group of 3, which is 7, 7, 13, 14. 7, 13, 14, 7, 13, 14. And lastly, a group of 4, which is 15. This is where you start with the tabular method. Step number 1, done. I can as well represent the binary representation. Represent these minterms. This is 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 6, 8, 1. This is 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1. This is 1, 1. This is 1, 1, 1. This is 1, 1, 1, 1, 1. Right. Pana rasigere so far. Patir pana. Pana rasigere so far. Nope. It means all is well. We go to step number 2. Step number 2, introduce match the pairs. compare the groups n and the groups n plus 1. A meshed pair is a pair which differs by one variable. Step number 2, we introduce the meshed pairs, right? Meshed pairs are found by compare groups n and n plus 1. What are you comparing? A meshed pair, MP. A meshed pair differs by one variable. All right, we go to our table. We compare groups n and groups n plus 1. So if this is group 0, this is group n plus 1. If this is group 1, this is group n plus 1. So I'll be comparing this group and this one, and this one, this group and this group 3, and group 4. Right. I find the meshed pairs. So these are our meshed pairs. Let's find the meshed pairs. Meshed pairs are found by finding a pair which differs by only one variable. A pair which differs by only one variable. So if I compare this min term 0, 0, 0 and 0, 0, 1, only one variable changes there. Here, this variable changes. Only one, the rest remains the same. It means the min term 0 and the min term 1, they are a meshed pair. It means min term 0 and min term 1 are a meshed pair. So our first meshed pair, we have, this is no longer necessary. For our first meshed pair, let me do this. We had this group, we had this one, we had 3, this, and lastly, this one. So for our first meshed pair between groups 0 and group 1, we have min term 0 and min term 1 being a meshed pair. We then compare the min term 0, this one, with min term 8. Is it a meshed pair? These three variables remain the same. Let's do this. 1, 2, 3, 4. Right. Only one change here. It means the min terms 0 and 8 are also a meshed pair. And that's it. That's it for our two groups. Let me do this. And that's it for our two groups. We then go and compare these two here. The first ones with this one. The second ones, we start comparing 0, 0, 0, 1 and 0, 1, 1, 0. This one and this one. How many variable changes do we have? I have 1 here, I have 2 here, I have 3 here. This is not a meshed pair. It means variables for the min terms 1 and 6. It is not a meshed pair because there are more than one variable changes. Directly looking at the numbers, you now know the procedure. Directly now looking at the numbers so that we finish up quick. I then compare. I started with comparing 1 and 6. I then compare 1 and 9. Is 1 and 9 a meshed pair?
Nope.
Nope.
Yes.
Yes, it is a meshed pair. Only one variable change, 1 and 9. Is it? Nope, it is not. There are two there. 0, 0, 1. 1 and 9, they are a meshed pair. Excuse me, there is a 1 here. Don't know why I removed it. All right. 1 and 9. This one and this one, they are a matched pair. Only variable change here. The rest, they are the same. All right. We also have 8 and 6. Are 8 and 6 a matched pair? Eight and
No.
6. 1, 2. Nope. 8 and 9.
Yes.
8 and 9, they are a matched pair. So we are done with these two. We then go to 8 and 9. This is another matched pair. This is 8 and 9. So we have another matched pair here. We then go to this group here. So 6 and 7.
Matched pair.
It is a matched pair. 6 and 13. It is not.
No.
6 and 14.
No.
Yes.
Yes.
Matched.
6 and 14 is a matched pair. Then we have 9 and 7.
No.
Nope. 9 and 13.
No.
Yes.
Yes. We have 9 and 14. No. That's another no, 9 and 14. So we have these ones here. We go to the last n, 6 here, right? Right. We go comparing the last ones. So 7 and 15. Yes.
Matched.
7 and 15. We have 13 and 15.
Yes.
Then 14 and 15, they are all matched pairs.
Yep.
These are our matched pairs. Now we go to their binary representation. Binary representation. We then go to to their binary representation. All right. How do I find the binary representation of a matched pair? Let's look at 0 and 1. When I compare the 0, this is 0 and 1, 0, 0, 0, 1. I found out this is the matched pair. The binary representation, it will look like this. 10 minutes, 1, 2, 3, and a dash where there is a change in the variable. So for this 0 and 1, 0 and 1 pair, we have 0, 0, 0, dash. This is my binary representation. If we do the same for 0 and 8, this is 0 and 8, it is dash 0, 0, 0. 0 and 8, this is 0, this is 8. There was change in the first bit, so it begins with a dash, then the rest remains the same. This is the binary representation for 0, 1 and 0, 8. All right, for 1 and 9, we continue. Those who understood what I just said, participate. 1 and 9, what is the binary representation for 1 and 9? 1 and 9. Dash
Dash 0, 0, 0.
0, 0,
Dash 0, 0, 0.
0, 1. 8 and 9. 1, 0, 0, dash. 1, 0, 0, dash. We are done with this. Then we have 6 and 7. 0,
0, 1, 1, dash.
1, 1, dash. 0, 1, 1, dash. 6 and 14. Dash 1, 1, 0. 9 and 13. 1, dash. 9, 1, dash. 0, 1. This is 9 and 13. Then we have 7 and 15. Dash 1, 1, 1. Dash 1, 1, 1. Then we have 13 and 15. This is 1, 1,
1,
dash 1. So this is 1, 1, 1,
1, dash.
dash. There we have our binary representation. Right. Before we continue, I think we have 7 minutes. Before we continue, there is another, let's put another point to note. You need to tick each used min-term. Tick each used min-term. You need to tick each used min-term. So if we start here, min-terms which were used beginning here, we have 0, 1, 8, 6, 9, 7, 13. All of them were used in the function f. When we go to MP1, 0 was used here, 1 was used here, 8 was used here. 6 was 6 used somewhere? 6 was used here. 9 was used there, is there. 7 was used here. It will be very useful when identifying our prime implicants. You can as well do this process at the end, but I'm just doing it now because of my time. So 7, it was used here. 13 here. 14 here. 15, it was used down there. So at this stage, all the implicants were used. All right. We have 5 minutes, so I'm ending the video and we continue from where we left off here. So let me screenshot this so that we can use it later on. Okay, I'm ending the meeting. We continue soon after. We are not waiting 5 minutes. We continue soon after, then we finish up that table.